Hey everyone, and welcome back for another deep dive.
Mm.
Today we're going to be tackling something truly mind-boggling.
Okay.
Black holes.
Oh,
I
yeah.
know, it's a big one.
Yeah, it is.
And, you're probably curious about what lies at the heart of a black hole. And we have this fascinating article from the Brighter Side of News that's packed with insights about it. It talks about how scientists are using quantum computing and deep learning,
Uh-huh.
you know,
Yeah.
these cutting edge technologies to
Okay.
try and figure out what's going on inside these gravitational giants.
Yeah, it's like trying to peek behind the curtain
Yeah.
of the event horizon, something that was basically impossible before.
Right.
These new techniques are really letting physicists tackle
Mm-hmm.
questions that have been stumping them for decades,
Yeah.
you know?
It's so cool.
Yeah.
All right, let's dive in. This article keeps mentioning the holographic principle. It sounds like science fiction to me, honestly. Is this really a thing?
Well, it's definitely a real scientific concept
Yeah.
and a really mind-bending idea
Yeah.
in physics. Imagine this. Everything about a 3D black hole could be represented as a 2D projection, kind of like a hologram.
Wow.
All the information is encoded on its surface.
So you're saying that the 3D reality is like an illusion?
Yeah.
Created by information on a 2D surface?
Yeah.
That's
No.
pretty hard to wrap my head around.
Yeah, it is a tricky concept.
Yeah.
And some physicists believe that our entire universe might be a holographic projection. It could completely change how we understand reality.
Oh, okay. So that's a huge idea.
Yeah.
But before we go too far down that rabbit hole, the article mentions two big theories of physics,
Okay.
Einstein's general relativity
Right.
and the standard model of particle physics. Can you remind me what those are all about and why they seem to clash when we talk about black holes?
You got it. General relativity explains how gravity works. It's all about the curvature of spacetime caused by massive objects. It does a great job explaining things on a large scale, like the orbits of planets. But the standard model is all about the tiny stuff,
Right.
like particles, and the forces that govern them. It's amazing at explaining the subatomic world.
Okay.
The problem is these two theories seem to break down when we try to apply them to extreme environments, like black holes.
Ah, so black holes are like the ultimate test for our understanding of physics.
Precisely. They're where gravity and quantum mechanics really clash, and that's
Yeah.
why physicists are so fascinated by them.
Okay, cool. Now, the article also mentions these quantum matrix models, which sound pretty complicated.
They are,
What are those and why are they important?
for this research, think of quantum matrix models as mathematical representations of particle theory, like a code that describes how particles interact. And here's where the holographic principle comes back in. These matrix models can also give us insights into gravity. The math describing particles on that 2D surface can be translated into the math describing the 3D gravity of the black hole.
Oh, wow. So if scientists can crack the code of these models, they can learn about what's happening inside a black hole.
Exactly.
That's amazing.
A key thing that they're trying to figure out is the ground state of these models, which is the lowest energy state of a system. It's like finding the most stable configuration. By understanding the ground state of a matrix model, we can reveal secrets about the black hole itself.
I'm guessing this is where quantum computing and deep learning come in.
You're absolutely right.
These models must be incredibly difficult to solve.
They're super complex, and traditional methods really struggle.
Yeah.
Especially as the models get larger. But quantum computers, with their ability to, take advantage of the weirdness of quantum mechanics,
Yeah.
have the potential to solve them much faster.
Wow.
They can handle problems that would take regular computers billions of years.
I read that they describe these quantum circuits as being like a musical score.
Yeah.
Can you explain that a bit more?
It's a great analogy. Each wire in the circuit represents a qubit, which is a quantum bit of information. And the gates in the circuit, which are quantum operations, are like the notes in a score. By arranging these gates in just the right way, they can create a quantum algorithm to solve the matrix model.
Oh, that's so cool. So it's like composing a quantum symphony to unlock the secrets of a black hole. That's incredible.
Yeah.
But what have they actually found using these techniques?
Well, in this particular research, they were able to determine the ground state of two matrix models using quantum computing and deep learning. And that's a big deal. They weren't just able to calculate the energy of the ground state. They were able to map out its entire structure, something traditional methods have a lot of trouble with.
Wow. So what does that tell us about black holes?
Remember that link between the matrix models and black holes?
Right.
Understanding that ground state could reveal what's happening inside a black hole even behind the event horizon.
So we're actually getting closer
Yep.
to answering one of your first questions. What's at the core of a black hole?
Right.
But before we go further, can we take a step back and talk about the anatomy of a black hole?
Absolutely.
I want to make sure we're all on the same page.
Let's start with the singularity, the point at the very center of the black hole.
Okay.
It's where all the mass is concentrated.
Yeah.
And where density becomes infinite.
Okay, and I know the singularity is surrounded by the event horizon, that point of no return.
The event horizon is the boundary, beyond which nothing, not even light, can escape the pull of the black hole. If we could somehow see a black hole up close, the event horizon is what we would see as its edge.
Okay, what about all that gas and dust we see? Swirling around black holes in those incredible images.
That's the accretion disk. It's a disk of material spiraling inwards towards the black hole, drawn in by its powerful gravity.
Okay.
The material gets heated up as it swirls, causing it to glow brightly. That's how we can actually detect black holes.
This article also mentioned something called Doppler beaming.
Yes.
Which sounds intense.
That is.
Can you explain that to me?
Imagine you're looking at a cosmic spotlight. When the material in the accretion disk moves towards us at incredible speeds, close to the speed of light, its light gets compressed and appears much brighter. This is Doppler beaming in action, and it's a direct result of Einstein's theory of relativity.
So we're seeing the effects of relativity in these black hole systems.
Yes.
That's wild. What about this ergosphere thing?
Okay.
What's that all about?
The ergosphere is a region found around rotating black holes. It's outside the event horizon, but it's a zone where space itself is being dragged along by the black hole's rotation.
Wait, so you're saying space itself is swirling around the black hole?
Exactly.
In a cosmic whirlpool?
And here's what's interesting. Objects can still escape. The black holes pull from within the ergosphere if they gain enough energy from this swirling space-time.
Okay, that is definitely weird. It seems like the closer you get to a black hole, the stranger things become. And then there are those powerful jets we see shooting out from some black holes.
Ah, yes, the jets. These are beams of superheated matter and radiation that blast out from the poles of some black holes, often at nearly the speed of light. They can stretch for thousands of light years, and they can even affect the evolution of entire galaxies.
Wow.
We think these jets are powered by the intense magnetic fields around the black hole and its accretion disk.
So black holes aren't just about sucking things in, they can also shoot stuff out with incredible power.
Yeah.
I'm starting to see black holes in a whole new light. Before we move on, could you quickly recap the main parts of a black hole for our listeners?
Sure. At the center, we have the singularity, the point of infinite density. Surrounding it is the event horizon, the point of no return. Then you might find the photon sphere, where light itself can be trapped in orbit. Many black holes have an accretion disk, a swirling disk of gas and dust. And some have an ergosphere, the region where space itself is dragged along. And then some blast out these powerful jets of energy from their poles.
Okay, so we've covered a lot of ground here, from this mind-bending holographic principle to the anatomy of a black hole. It's incredible to think that scientists are now using cutting-edge technology to try and understand what's going on inside these mysterious objects. We'll be back in a moment to delve even deeper into this research and explore some of the mind-blowing questions it raises about the nature of reality. Stay tuned.
Welcome back.
So before we went to break, we were talking about how researchers are using quantum computing and deep learning to study these incredible objects. But I have to ask, why should someone like me, who isn't a physicist, care about what's happening inside a black hole, billions of light years away?
That's a great question. And it's easy to think of black holes as being distant and irrelevant to our lives. But the truth is that understanding them can have huge implications for how we understand the universe and even our place in it.
Okay, I'm listening. Tell me more.
Well, for one thing, black holes are like extreme labs for physics. They push our current theories to their absolute limits, forcing us to really confront what we don't know. By studying them, we can test and refine our understanding of gravity, quantum mechanics, and the very nature of space and time.
So it's like black holes are helping us rewrite the textbooks on physics.
Exactly. And who knows what incredible new insights we might uncover along the way. The discoveries we make could have ripple effects throughout science, leading to advancements in other fields, maybe even things like material science, energy production, or information technology.
That's amazing. It's like a cosmic domino effect.
Yeah.
Understanding black holes could lead to all sorts of innovations we can't even imagine yet.
You got it. but it goes deeper than that, too. Remember that mind-bending holographic principle
Yeah.
we're talking about?
Right.
If that turns out to be true,
Yeah.
it would completely revolutionize how we understand reality itself.
Let's revisit that idea. How could the holographic principle change our view of the universe?
Well, if our universe is just a holographic projection, a cosmic shadow play of information encoded on some distant surface, it raises some pretty profound questions.
What?
What does it mean for something to be real if it's just a projection?
Yeah.
And what is projecting it? Is there some higher dimensional reality out there that we can't even perceive?
Whoa, those are some big philosophical questions. It's like something straight out of the Matrix.
It really is.
Yeah.
The holographic principle challenges our most basic assumptions about the nature of reality. It suggests that what we perceive as a three-dimensional world might be an illusion.
That's both fascinating and a little unsettling. It makes you question everything you thought you knew about the universe.
Absolutely.
Yeah.
But that's what's so amazing about science. It constantly pushes us to expand our minds and consider new perspectives. The holographic principle, even if it's not totally accurate, forces us to confront what we don't know.
Right.
And consider possibilities we might never have dreamed of before.
I love that idea. Even being wrong can open up whole new avenues of exploration.
Yeah.
But let's come back to black holes themselves. This article really focuses on what's at the core of a black hole.
Right.
Have these new research techniques actually provided any answers? What have scientists learned about what's inside?
That's the big question, isn't it? To peer beyond the event horizon and see what's really there. We're not quite there yet. But these new techniques using quantum computing, deep learning, are giving us tantalizing clues. Remember, they allow scientists to probe the structure of the ground state of quantum matrix models, which can translate into information about the black hole itself.
So it's like creating a mathematical map of the black hole's interior.
That's a great way to put it. By studying these maps, scientists hope to untangle some of the biggest mysteries about black holes. What happens to matter as it falls in? Does it get